And now I want to discuss the general categorical theory of isomorphisms. So let C be a category, and X and Y objects of C. And F from X to Y is going to be a morphism. So an inverse for F is morphism in the opposite direction, a G from Y back to X, with the property that G composed with F is going to be the identity morphism of X, and also F composed with G is the identity morphism of Y. Okay, so it has to be inverse both ways around. Okay. And note that this is kind of symmetric, that means F is an inverse for G. Right? G is an inverse for F if and only if F is an inverse for G. And we say F is an isomorphism if it has an inverse. So, and then we say X and Y are isomorphic if there exists an isomorphism. And if so, then we write this kind of symbol here to indicate isomorphism. So, so one kind of key fact that we need to notice about this is that if F has an isomorphism, then it's going to be unique. So there's a little lemma. So F has an inverse, then it's going to be unique. So let's suppose G1 and G2 are both inverses. Okay, so that means we've got 4 properties. That G1 composed of F is the inverse identity for X, and F composed with G1 is the identity on Y, and the same 3 and 4 the same for G2. Okay, and so from these we want to deduce that G1 equals G2. So let's look here at G1 composed with F composed with G2, and let's distinguish. There's kind of two variants of this, but they're kind of the same. So these two are the same, of course, by the associativity axiom. One of the axioms for a category is that composition is associative. And then on this one here, then we've got G1 F composed with G2 by this property 4 here is going to be G1 composed with the the identity on Y. So this was equation 4. Or going over to the left here, right, so here we've got G1 composed with F, but G1 composed with F by equation 1, that's the identity. Then over here, G1 composed with the identity is just G1. This was one of the two identity axioms. And similarly, the id x composed with G2 is equal to G2. This is again the identity axiom. So putting this together here, we've got G2 is equal to G1. Well, that's what we were claiming. We're claiming that the inverse is unique. If G1 and G2 are both inverses, then they're the same. We can unambiguously write F inverse, or the inverse of F. Okay. Of course, not every morphism has an inverse, but if it does have an inverse, then it's unique, and we call it F to the minus 1. Examples of how this works out. In the category of sets, the isomorphisms are just bijections. And in the category of groups, isomorphisms are just bijective homomorphisms. But that's not completely obvious. There's a kind of lemma behind this fact here, and the lemma is that if let's say alpha from G to H is a bijective homomorphism, so then because it's a bijection, you've got a function in the opposite direction, alpha inverse from H to G, and it's kind of a key point that that's also a homomorphism. Okay, so that's not 100% obvious, but it's a fairly easy exercise, a standard fact. Okay, and using that, it's easy to see that like I say, the isomorphisms are exactly the same as the bijective homomorphisms. And similarly, in the category of rings, say, or any of the other similar sorts of examples, isomorphisms are bijective ring homomorphisms. Yeah. And then finally, in metric means the category of metric spaces, and also in category of topological spaces, the isomorphisms are homeomorphisms. And that was essentially how what we defined homeomorphisms to be. And so those are isomorphisms in various standard categories. So now here's another little lemma that we'll need. Firstly, just that identities are isomorphisms. The inverse of the identity is, of course, just the same, the identity again. Secondly, so F's an isomorphism from X to Y, then so is the inverse map F inverse from Y to X. We've actually kind of remarked that already. Thirdly, so we've got two isomorphisms, F from X to Y and G from Y to Z. And I want to claim that the composite G composed with F from X to Z is also an isomorphism. And here, okay, let's just say what the inverse map is. The inverse is just F inverse composed with G inverse. So for C, well, you've got G composed with F, composed with F inverse composed with G inverse. And so that by associativity of composition, that's G composed with F inverse composed with G inverse. And then F composed with F inverse is the identity, so that's G composed with the identity composed with G inverse. But composing with the identity doesn't do anything, so that's G composed with G inverse, which is the identity. And similarly, we do composition the other way around. And so again, so by associativity, that's the same thing as we collect the G inverse with the G together there. That's F inverse composed with the identity composed with F, which is, and then composing the identity doesn't do anything, so that's F inverse composed with F, which is the identity. Okay, so that proves that we've got an inverse for G composed with F. So that proves this lemma here. Now, as a corollary of that, we want to prove that this relation of isomorphism is actually an equivalence relation. So you need to prove it's reflexive, that X is isomorphic to X, and of course it is, because the identity is an isomorphism from X to X. And so if X is isomorphic to Y, in other words, there is an isomorphism from X to Y, then there's also an isomorphism in the opposite direction, just by taking the inverse of the first one, and see if X is isomorphic to Y and Y is isomorphic to Z, then X is isomorphic to Z. To prove that, of course, we just choose isos f from x to y, g from y to z, and g composed with f from x to z is iso. So this proves that the relation of being isomorphic is an equivalence relation. And then one more basic fact that we need is the interaction between this and the notion of functors. So suppose for f from x to y, and isomorphism in C, and that capital F from C to D is a functor, then I want to claim that, remember, functor can apply it to objects. We get objects fx and fy. We apply it to morphisms. We get a morphism ff from fx to fy. Okay, so I want to claim that it's an isomorphism in D. So we're claiming that it's got an inverse, and how do we get the inverse? Well, we just apply f, capital F, to the inverse of the original morphism, f inverse. And so the proof, well, we want to consider ff composed with f of f inverse. Well, that's one of the first axioms for a functor is that it respects composition. So this is f of f composed with f inverse. But that's f of the identity because, that's what we mean by the inverse, that f composed with f inverse, both either way around, should just be the identity. So that's f of the identity, which is the identity. That's the other axiom for a functor. Functors have to preserve composition, which is what we used here, and they have to preserve identities, which is what we proved here. And similarly, f of f inverse composed with f of f is f of f inverse composed with f, which is f of the identity, which is the identity again. So we see that isomorphism, functors send isomorphisms to isomorphisms.